understand something really important there. And this is something like if there's physics students listening right now, they got to listen really closely here, because this is the part of their course that they will not be taught. Okay. And it's really critical. So how did quantum mechanics start? It started with Max Planck trying to make a better light bulb. He was commissioned by, a group of different organizations that were trying to improve on the light bulb, because the light bulbs didn't last very long then. The filament kept on burning out and all this. And so Max looked at it in detail and tried to figure out the thermodynamics of this element that emits electromagnetic fields when you heat it up, right? So he was looking at it, and the equations of the time were saying something really weird. They were saying that like the element should emit infinite amount of ultraviolet radiation, and that's not what we were measuring in laboratory. Mm-hmm. So it was called the ultraviolet catastrophe. So he tried to resolve it. And in order for the equation to work, it's called Planck's law, he had to add a little component, a little free parameter in some ways, that he called h bar. And what it did is that in the equation, it basically said that like the electromagnetic field that's radiating from the element when you heat up something is actually coming out in packets, little spinners.
Like pulses?
Yeah, like pulses, packets. It wasn't continuous.
Right.
Like quantas of energy, which were described by H or H bar later. And that packet of energy, eventually Einstein took that and said, hey, I can explain the photoelectric effect with that. So that like the little packets of energy are hitting electrons and throwing electrons out in semiconductors. And that is what makes, like photocells that we use for, solar panels. Mm-hmm. And he got the Nobel Prize for that, calling the little packets photons. And that's where the concept of photons come from.
Okay.
You see? And so, when you looked at this equation, Planck's law, it said that the universe, when it radiates electromagnetically, it's packets of energy that it's radiating, and it's absorbing packets of energy. The equation is describing an oscillator. Okay? That is the foundation of quantum mechanics, is the description of an oscillator. So you could think of it as a little proton, like the nucleus of an atom, or an atom being an oscillator, right? And the problem is that, okay, so listen to this. This is remarkable. So when it's taught to students, instead of telling the student, visualize a little spinner, a little top spinning, that's an oscillator, right? They're told to visualize a spring with a weight on the end. They're mathematically mappable one to the other. So it's mathematically the same. Except that if you're thinking the universe is making springs with weights on the end, you don't have the correct image in your head of what you're actually describing in your equation.
Right.
And these type of analogies are very destructive to our capacity to actually understand the universe. Because we start, making models in our head that don't have anything to do with reality. Mm-hmm. Right? The universe is clearly not doing springs with weights on the end, right? Like a little spring that's oscillating up and down like this, right? And that's like critical that the students get the right visual. We're talking about something that's spinning.
Mhm.
I mean, springs with weights on the end are made by the universe after they've made the humans that makes the springs and the weights. Okay?
Right.
But if you're trying to understand the universe, then you got to have the right image in your mind.
So if I'm trying to visualize this, and I think, I'm picking up what I was able to understand from an interview that I watched you do. And basically what you're saying is this pulsing, oscillating pattern is that we're creating a new projection of reality, so to speak, in every Planck second, which is like the smallest measurement of time possible. It's the interval between these pulses.
Exactly.
And
there's
it's
a timing thing that's
Yes,
happening.
it's like boom, 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 but so fast. And
There's a heartbeat
and it's
to the universe.
and it's almost infinitesimally measured, and it's creating reality in every Planck second.
Exactly. And then as you go up in scale, that timing slows down, right? Because it takes longer for a proton to make a turn than to a Planck, which is billions of times smaller.
So a Planck is like a quark? Or is it smaller than a quark?
Smaller than a quark.
Okay, so it's the very basic unit that
of creation.
The irreducible unit is like a Planck.
It might be reducible to sub-Planck,
Oh boy.
but the speed of light limits. So you could say that maybe it's the fundamental pixel for our size universe.
Okay.
But
it may go all the way down
That's right.
infinitely.
Yes, because past the event horizon of a black hole, you have, it's called transplanckian problems, meaning you have things that would go faster than.
And so when I read verse 4 of the Tao Te Ching, it says, "The Tao is like a well, used but never used up. It is like the eternal void filled with infinite possibilities. It is hidden but always present. I don't know who gave birth to it. It is older than God."
And that's great.
And
that's amazing.
And to me that feels like what the Tao is describing is this fundamental unified field.
That's right. And that field, this is what the students will not be taught. Okay? That field was actually discovered by Max Planck while he wrote these equations. Mm-hmm. The Planck law has a little bit that was removed from it, okay, that described just what you read.
Mm-hmm.
Because, so now when you solve Planck's law for the internal energy of the oscillator, okay, there's a part of the equation, 1/2 h bar mu, or it can be omega, depending if you're doing how you write the equation, but which says, so let me back up. The equation says at this temperature, you get this spectra of heat. Okay, meaning at this temperature, you get this amount of energy from the oscillator, right? So you get a spectrum, right, of and you see that when you buy a light bulb still, it'll say 3000 K on it, right? 3000 Kelvin. That is the temperature of the light bulb, the energy radiance of that light bulb. Okay.
And I suppose you can measure that as heat or light, like lumens or kelvins.
Emission from
right.
the filament. Nowadays, light bulbs are made of diodes, so we have that convention to describe the color of the photons emitted by the light bulb still, but it's actually not coming from a filament anymore, right? Mm-hmm. However, this fundamental equation that describes this, so it got rid of the ultraviolet catastrophe problem. It gave the right answer for the ultraviolet emission and all this. When you solve it, it tells you, there's a part that tells you that at 0 Kelvin, so on your graph, on your spectra, 0 Kelvin would be like the ground state of the electromagnetic field, right? When zero emission should happen.
So that's the cessation of all energy.
Yeah.
At 0 Kelvin, there's nothing.
0 Kelvin's like, have you been to Canada?
I've been to Edmonton.
Okay.
Yeah, it's fucking cold.
It's damn cold, right?
Feels like 0 Kelvin.
Yeah. Well, it's not anywhere close to 0
Of
Kelvin,
course,
right?
of course.
And so 0 Kelvin is seriously fucking cold, right? So nothing should move.
Absolute. Yeah.
There should be no thermal agitation. There should be no energy.
Mm-hmm.
However, the equation, which gives all the right answer for the rest of the stuff, says that at 0 Kelvin, there's an infinite amount of energy. The equation diverges to infinity there.
Mm.
And
So it's almost like at 0 Kelvin, we're back to the Tao, which is completely full with infinite possibilities and infinite energies. It's like a
Exactly.
point of singularity.
Exactly. And you said the word singularity, which implies Einstein field equation. So let's hold that.
Okay.
You got the right idea.
Yeah.
Now you have but you say, okay, so yeah, so that means the ground state of the electromagnetic field is full of energy.
Mm-hmm.
When Max Planck discovered this, he called it 0 point energy, 0 Kelvin energy, right? And so 0 point energy was like, oh, what do we do with the infinite amount of energy, right? Well, in general. Now, was this done on purpose? Was this done just because we didn't know what to do with the infinite amount of energy, whatever? I would say probably a little bit of both, and I've done a lot of research in history of physics. You have to put it in the context of the time. We're talking, First World War, Second World War. We're talking about, looking for atomic energy, the atomic bomb being developed, giving the world the impression that there was an infinite source of energy that could be accessed might have been not necessarily what people wanted to do at the. What happens when you remove it is your equation now is describing an oscillator without a source. So it's spinning. So now let me ask you, your wheels on your car, which is an oscillator, right? It's spinning thing. Okay. Do they go anywhere if you don't put energy in it?
Only if I'm on a downhill.
Yes. Then you're using the gravitational field
yes.
to put energy in the system, right?
Right.
So that's called a gravitational potential. If they're on flat, they don't go anywhere until you put energy,
Correct.
right? So you have to put energy in an oscillator for the oscillator to continue to oscillate, right? Let's go back to the spring and the weight.
Yeah, like how does an atom spin?
All right.
Where's the energy source that keeps all atoms spinning, all electrons moving? Where is that? Where does that come from?
Dude, they get on the case of people that have been working on what they call free energy or over unity devices all the time, saying you guys are trying to violate the laws of conservation of energy and da. This is a violation, like right in the base of quantum mechanics. There's a violation of the laws of conservation because your oscillator, go back to a spring and a weight, if you stop doing this, what happens? Does the spring continue oscillating? Yeah, for a minute or two, but then it stops, right? So the same thing, and when you calculate it, it's inconsistent mathematically, meaning like this field, okay, that's the 0 point energy is described as like constructive and destructive waves of the electromagnetic field, right? And if that was all canceled out, it would be, technically it's called commutative. The equation cannot be commutative, meaning it has to be non-commutative. That means there's got to be more energy that comes in to overcome the resistance of the oscillator to continue to oscillate.
Right.
Just like you have to put energy in your motor
Right.
for your wheels to keep, against the friction and the weight that it's pulling and all this stuff.
So this is like a revelation that seems like right in front of our eyes. So there's been a quest to create a machine that could perpetually move, a perpetual motion
Yeah.
machine, which doesn't require additional energy
Yeah.
to add it. So you start the momentum, and then once you start the momentum, it goes infinitely, right?
Yeah.
Like that's been a scientific study, but it's happening all the time with every single atom.
Exactly.
It's in perpetual motion without
Exactly.
the adding of additional energy. So the only
Did
thing
you
that
ever
can
receive a bill
possibly,
for it?
yeah, the only thing that could possibly explain it is there's a source of infinite energy at the root of all of that.
And we found it. And then it was ignored. It's 100 some years later.
And yeah, because at the core of everything is infinite energy. So if you somehow unleashed the core of everything, you would get the destruction of everything.
But that's the other thing. When you create fission, right? You're liberating massive amount of energy from a very small amount of matter.
Mm-hmm.
E equals mc squared on matter is a lot of energy.
Yeah.
And so this is remarkable. Where is this energy coming from? In the movie Oppenheimer, I was proud of them for at least mentioning, it's very quickly mentioned, that it's the strong force. It's the force that's holding the atom together that's being liberating.
Mm-hmm.
But the mass of the protons that make up that nuclei, right, protons and neutrons, is not given in standard physics. So I'm not going to want to get too technical here. But
Yeah.
I will get back to the mass of the proton.
Mm-hmm.
But you have to understand that currently, in a very non-rigorous way, the mass of the proton, which is the mass of matter, how matter has energy, how matter has mass, is not given in physics.
Mm-hmm.
It is no equation, analytical equation that says, it just says that it's the result of the strong force interacting,
Mm-hmm.
which is not, the source of which is not given. Yet, so this is what I did in this paper.
Mm-hmm.
I went through, I said, okay, you can't remove this 0-point energy. It's mathematically and physically inconsistent.
Mm-hmm.
Everything should have stopped a long time ago if there's no source to the oscillator, right?
Right.
And then I calculated with what's called correlation functions. They're equations that describe in a field of waves, like think of the surface of the ocean, how many are gonna cancel out and how many are gonna be constructive.
Mm-hmm.
And because the equation is non-commutative, that means that there's actually, it's not the same. A photon that's absorbed into the oscillator and emitted is not the same as a photon that's emitted and absorbed. So you end up with a positive energy,
A surplus, yeah.
a surplus. So I calculated the correlation function of this field for an object, and so you put in there the correlation time. It's like the scale at which you're looking. When you're looking at the waves, there'd be bigger waves, smaller waves, smaller waves, smaller waves, right? So you put in there the scale you want to look. And when I look for the Planck, I got the Planck mass. But when I look for the proton, I got the proton mass.
Mm-hmm.
The whole thing.
Mm-hmm.
Showing that the mass or the energy of matter, which is the proton, right, is coming from this field.
Yes.
You see, this is remarkable.
Mm-hmm.
It's remarkable because the Standard Model has this whole Higgs mechanism, that gives mass to particles.
Right.
They called it the God particle, right? They spent some $13 billion building accelerators to find it. It costs $1.5 billion a year budget to keep that thing going. And, and at the end, the Higgs mechanism in the Standard Model is only consistent inside the Standard Model. When you go to experiment to verify it, right, for the proton, you're predicting less than 1% the mass of the proton, 5 to 1% the mass of the proton. And then if you add that to the fact that we're missing 96% the mass in cosmology, then you're only predicting like 0.1% of what we see, right?
Yeah. Okay. So this is coming to me here, and I need to I need to step back to something you said.
Okay.
You said the universe is expanding. So
Yeah.
the universe is both mass, light, energy. So would that be correct to say that the universe is energy roughly in different ways?
In different ways. It's 99.9% plasma.
Okay. So
And whatever is not plasma is plasma that's cooled off.
Okay. So if it's expanding,
Yeah.
then there's something beyond the horizon.
Very good.
There's something beyond the horizon. What is it that's beyond the horizon that we're expanding into? What is that? Is that
Most likely a larger universe.
Whoa. Okay, so we're expanding. It's a universe of a different type.
No, just a larger universe. Think of a galaxy inside our universe, right? It expanded from a quasar, like it became a galaxy expanding inside our universe.
So then when the Tao Te Ching is saying that the Tao, which is the unified field of all universes must come from the unified field, right?
Right.
So all universes maybe we say God is our universe, right? And they say the Tao is older. than God.
Then they must be talking about the universe our universe is in.
Yes.
That's
They're
right.
talking about the great universe.
Right, which is probably in a larger one again, and a larger one
And
again.
infinite, but that's all still the Tao.
So, yeah.
Yeah.
So now you have the concept of fractality, singularity,
Right.
right?
So God is describing our universe. Our universe is all contained within the substrate of a unified field that we call it the Tao.
Yeah.
I like to call it the force, but whatever that is, we're just one fractal of that.
That's right. And that field of energy, it's coming from all these oscillators. Think of our universe as an oscillator it's spinning to, and everything in it is oscillating. The field of energy has got all these oscillation in it.
Infinite possibilities.
That's right. Infinite oscillations.
Yeah.
Infinite amount of energy. Infinite amount of energy. And even if you just say, okay, well, I'm going to cut it off at the Planck scale because that's the speed of light, whatever, like we show in the paper that there's a good reason to use the Planck scale as a cutoff. When you still have 10 to the 93 grams per centimeter cube. So if you took all the stars we see in the universe and the black hole, everything, and we stuck it into a centimeter cube of space, we would be 39 orders of magnitude not as dense as 10 to the 93 grams. So it's like insane amount of energy is present in each centimeter cube of space.
Wow.
And that's what's running our world.
Yes.
And it's been there for 100 years in our equations.